Hello everyone, Aaron here, and welcome back to Leetcode. Today we are doing the N-ary tree level order traversal. Given an N-ary tree, return the level order traversal of its nodes' values. N-ary tree input serialization, that's just for test cases, I don't care. So the idea, I think, is, so 1 is the first layer, 3, 2, 4 is the second layer, 5, 6 is the third layer. So down here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You see it split like that. So the other day I was doing a problem involving a breadth first search. Well, it wasn't a breadth first search in the end, but I thought it might be. And I had trouble splitting the layers. I've been thinking about how to do that, and I think I have a solution. So this is going to be a breadth first search problem. And the reason I think it's going to be a breadth first search problem is because this is literally how breadth first search is defined. It goes through in layers. So the layer is 0. The queue is a deck that starts just with the root in it. In fact, let's result is empty, current is also empty. Then, in fact, I want to say the root is at layer 0. Then while there's anything in the queue, what I want to do is I want to say the node and the layer it came from is queue.pop left. And then if L does not equal layer, result.append current. Otherwise, what I want to do is I want to set current. In fact, let's do this. Current equals empty, and then current.append node L, layer equals L up here. So the thinking here is that if I've got something that is not the layer I'm focusing on, I've obviously stepped down. So the things I was collecting in the current are now finished. So I'm going to stick those in the result, and I'm going to reset that and say I'm now looking at this layer. Otherwise, or in fact always, then I'm going to put the current node in the current layer that I'm looking at. Then node.val, in fact, is what's going to go into current. Then for child in node children, what I want to do is I want to do queue append child L plus 1, because the children are obviously at one layer deeper than what the current node is. And then at the end, I want to do if, in fact, no, there will always be something to put into it. So result.append current return result. So this is basically just a standard breadth first search with this one little quirk about keeping track of what layer we're in. So let's do a quick trace with this guy here. So we start at layer 0, the result is empty, the current is empty, and the root gets thrown in associated with layer 0. Let's take something off the queue. We're going to take this 1 off the queue. We're going to see its layer is 0. Its layer is equal to the current layer, so we're not going to deal any of this yet. We're just going to stick 1 in our current layer. For each of its children, the 3, the 2, and the 4, we're going to put those into the queue, and we're going to say they live at layer 1. We're going to go around again, and we're going to take off this 3, and we're going to say, well, that does not have layer 0, so we're going to take that thing we had in the current, which was just the 1, and we're going to throw it in the result. We're going to reset the current to be empty and set the layer to now be layer 1 that we're interested in. We're going to throw the 3 into the current things, and then we're going to go to each of its children, 5 and 6, and say they live at layer 2. Going back around, we're now looking at the 2. It's on layer 1, which matches the layer we're currently looking at. So we're going to throw it into the current queue. It has no children. We're going to take the 4 off. It lives on the current layer, so it's going to go into the current. So the current now contains 3, 2, and 4. It has no children. We go around. We take off 5. It is at layer 2. We weren't looking at layer 2. We were only looking at layer 1. So we're going to move the 324 list into the result and reset the current layer and say we're now looking at layer 2. Throw the 5 in there. It has no children. 6 goes in. It matches the current layer. So we're just going to throw 6 in. We're now done. So we need to throw everything that we need to take that current thing, that current layer that we just finished, put that in the result. So we're looking at 1, the 2, 3, 4, the 3, 2, 4, and then the 5, 6. And that is our result. Let's check if I've made any silly mistakes. I have made a silly mistake. So always 1. There we go. That looks promising. Let's use the other test case as well. Any other bounds we might be interested in? No, I think we're okay. Let's submit it, see what happens. There's just one little limit I was looking at there. Yeah, this is what I was slightly worried about. The 0 input. So here I was looking at this and I saw the total number of nodes between 0 and 10 to the 4. What would 0 nodes look like? And that is effectively this. I don't know what it's expecting. I guess just an empty list. This is a slightly misleading type. It reckons it can be a node, but it can be a node or it can be none. It's a nullable node. So kind of breaking the contract in this problem, which is a bit strange. But hey ho. It is what it is. Excellent. There we go. We are completely middle of the pack with memory use, so this is obviously the expected way to do it. We're quite slow, but then again, I think in Python, we're never going to be super fast. Excellent. Right, that's it for today. Sorry this one is coming at you so late. It has been a day for me. So thank you very much for watching. I hope you enjoyed. Remember to like, comment, subscribe, all of that good stuff. It really does help out the channel. And I will see you next time. Bye.